So for this problem at t equals 0 at origin in vacuum, the electric field has a magnitude of 3 and is propagating the z direction. We will be using right-hand circular polarization, and the k vector is equal to 3x hat plus 4y hat, and we're going to find the electric field and the H field. So starting off with the electric field, so our first component is going to be 3z hat, which is given, and then at t equals 0, cosine survives, so we're using cosine, and then omega t minus 3x minus 4y. Let's calculate omega t. So omega is equal to ck. C is the speed of light and k is a magnitude. So c is 3 times 10 to the 8th. 3 times 10 to the 8th. K is going to be, so the magnitude of k, so 3 squared plus 4 squared is 25, and then square root of that is going to be 5. And then we get omega t equal 1.5 times 10 to the 9th radians per second. And what else? So why we write negative 3x minus 4y? So say if we had y equals x plus 2. If we were to plot this, the line would be shifting to the left by 2 units. So it shifts to left by 2 units. So it's shifting to left by 2 units. It should be negative 2, but we write it as x plus 2. And so that's what we're still saying here. K is equal to 3x plus 4y, but we write it as negative 3x minus 4y. And we don't, so k is equal to 2 pi over lambda. Lambda is scalar, so it deals with magnitude and not direction. So that's why we don't have hats written over our 3x minus 4y. Okay, so then we have to write our second electric field component, so E2. This is going to be sine, and then the space and time components are identical. So k and omega are going to be the same as for E1. So omega t, we calculated omega t, but omega t minus 3x minus 4y volts per meter. Now we need to find, what else we had to write was the magnitude is 3. And that's because we're dealing with right-hand circular polarization. So for circular polarization, the magnitudes will be the same for both the components. So now let's find the direction. So we have our axes, we have our y, and we have our x. Our k is going to be this, and then into the board is defined as our negative, or into the board is defined, coming out of the board is defined as positive z, and that's where the direction of our E1 is. So if we put, so right-hand circular polarization, the thumb is going in the direction of the propagation, which is k, and the fingers curling mimics the rotation. So it would be going in this motion. So the second component has to be in that motion. So E1 is coming out of the board. It would land in the E2 would land in the 4th quadrant. So this is where E2 would be. and E1 and E2 have a 90-degree phase. So we would write it as 4x hat minus 3y hat over 5. And we use 4x hat minus 3y hat because k has a 3 to 4 ratio, so our E2 will have a 4 to 3 ratio. Okay, so I'm going to further explain why that ratio is true. So K is both perpendicular to E1 and E2 using the right-hand rule. So they're perpendicular to one another. We're going to define the angle between K and the x-axis as theta, and the angle between the x-axis and E2 as alpha. Both of these angles add to make 90 degrees. But the positive x-axis also makes a 90-degree angle with the negative y-axis. So if this is alpha, then this would be theta to make 90 degrees. And the same could be said about the other side. Okay, so to get the angle theta, tangent theta is equal to opposite over adjacent. So opposite would be this side, and then adjacent would be this side. So our adjacent equals 3, while our opposite is equal to 4. So this would be 4 over 3. Now let's look at our E2. E2, our theta, is right here. This is our opposite, and this is our adjacent. So adjacent was 4, so this is equal to 4. And then our opposite, adjacent was equal to 3. Sorry. Adjacent is equal to 3, and our opposite is equal to 4. So then that would be 4x hat, and then 3 minus 3y hat, and then this is the direction of for our E2 component. And then we actually have to divide by the magnitude of k, which in our case would be 5, because this is not a unit vector. And yeah, that's how we get 4x hat minus 3y hat as a direction over 5 as a direction of E2. And this is true for linear polarization and circular polarization, but it may not be true for elliptical polarization because the phase between E1 and E2 may not be 90 degrees. Okay, now we're going to find the H field. So E1 cross H2 will give our K. So we have E1 coming out of the board, and K is in this quadrant. So then H1 would result in being in the fourth quadrant. So if you use your right hand, E1 coming out of the board and E2 in the fourth quadrant will give the direction of H1. And then, so we could write that, so that's going to have a 4 to 3 ratio. So 4x hat minus 3y hat over 5. And then that's our direction, and then our magnitude will be 3 over 377. And we get this by H naught is equal to E naught over eta naught. E naught is 3 and eta naught is 377. And then cosine in our space and time components are identical to their E field. And then let's find our H2. H2, since E2 is in the fourth quadrant, K is in the first quadrant, so then H2 would result of being into the board. So if you use your right hand, do E as one finger and then H2, and then we'll give that K. So H2 is going into the board. So H2 is defined as being in the negative Z direction, negative Z hat direction. And then our magnitude is the same. And then sign and the same time and space components. And then the units are AM. And that is the answer to this example.